Jumbo, Hotep, hello guys. I hope that you are doing very well. So if you are discovering me in this video, I am Dr. Marcelin Inidabo. I am a PhD on control systems. I am an independent researcher and also a consultant in the industry. So today I am going to talk to you about second order ordinary differential equations, about second order systems that we use in the field of control systems. Of course, we'll talk about linear systems, but I will particularly talk about the temporal approach. I will not be talking according to the transfer functions, okay? So this is a second order, but of course there are some previous videos in which I have presented important information according to first order dynamic systems. And on that subjects, I have talked about the fundamental laws for autonomous first order systems, meaning that you move the initial condition out from its equilibrium, and then when you leave it, it comes back at a certain time to the equilibrium. So the second thing, fundamental laws that I have presented in that first video. So for the moment, the videos are in French. The previous videos that I am talking about are all in French, but of course I will take the time to put them in English, okay? And then when we check, so I said that I talk about the fundamental laws of autonomous systems and also the fundamental laws of an initial response for a first order system, okay? Following that, I introduced the notion of ISO time constant, meaning that if you consider the transient response, the transient part of the response of a system, might it be autonomous or initial, you can see that only focusing on that formulas that I'm sharing, meaning about the ISO time constant, you can compute at any given percentage of the equilibrium or final value or of the initial condition of your system. Okay, so most of the time when you consider a first order system, if you have the autonomous response, you can find directly on the graph, from the graph, the time constant at 37% of the initial condition. So you can fix there and find the time response, the time constant of your system. It is also possible to do the same thing when you look at an initial response and you put it at the 100% complement according to 37%, meaning at 63% of your final value. Okay? So after that, on the previous for the first order systems, I have talked also about ratios that I have introduced to do the identification of a first order systems. It is only based on the calculation of different time responses. For example, at 80%, according to the initial to the start time, okay, that you can divide to a given as a percentage. For example, I consider 90% of the initial condition for autonomous systems, and then I take the time at 10%, the 100% complementation of 90%, and then I do the ratio, and this ratio will give you a constant value. So you can find this information according to videos that I will prepare for you in English, but they are already ready, as I was saying, in French. Okay, you will be able to check if you want. And the last thing that I talked about is about the design of first order systems to reach or to achieve some temporal performances or some frequential performances according to a specific table that I propose you. And then from there, you can make your design of first order systems. This only in the context of the open loop systems. So now if you are ready, let's go for second order systems. Okay, so for this subject about the second order systems, they are given like this with this equation. And then here you can see that for a normal system, you have normally A0 here, but I just divide to see that we have here the static gain that we can observe here. And then all these elements like A1 over A2 can correspond to 2xc divided by omega n here. And then this term, as it is A2 over A0, you have this term which corresponds to 1 over omega n square here, okay? So from this, the literature in control systems is saying that in order to derive the solutions of your different systems, what you have is that you have the system here that is the damping ratio. This damping ratio is when it is less than 1. So you have three cases, okay? Three cases. Let me say it like that. You have three cases. For these different cases, what you have is that for these different cases, what we have is that when the damping ratio is less than 1, you have a given solution for your differential equation here. It is written like this, okay? When you move when you change this damping ratio, okay, when you take another value, the damping ratio is equal to 1, for example, you have the corresponding solution is here, right? And then for the final condition, for the final damping ratio, that is when the system is critically damped, what you have here is this solution. But let me tell you something. You can see that when you are solving this in terms of transfer function and when you determine all the poles of your system, meaning that the solutions of the denominator of your transfer function corresponding to a second order system, what you have is poles. The poles that you have two corresponding poles that corresponds to the solution of your system. If you look at it algebraically talking, you have the poles, okay, that are complex conjugated in this case because the discriminant of your characteristic equation is less than 0. Okay, so you have this solution. For the double solution of your characteristic equation, you have the solution of your differential equation. And then finally, for a critically damped system, you have this equation. Okay. Let us observe correctly what we have here. We have that here written as this. The first solution here is lying on a circular trigonometry, meaning that you have a sinus system here of this function and with an envelope that is an exponential function. Here, the system is living on a direct line, on a line, given temporal line here, always multiplied by the exponential here. And then finally, you have the system which is living in a hyperbolic trigonometry. That is what you have here, okay? Because you have a hyperbolic sinus here, and then it is multiplied by an exponential here, okay? So these two expressions are both quite the same, meaning that for xi less than 1 and for xi greater than 1, okay? And then for the first one, you have the expression is sinus, circular trigonometry, sinus hyperbolic trigonometry. And then the other difference is that you have the square root of 1 minus xi square here that you have, and then the other one is the opposite expression under the root that you have here, under the square root, okay? And then an exception is that, for example, for xi equaling 0, you have a perfect oscillating system. Notice that for these expressions, I have introduced the fact that, I repeat, I have introduced the fact that there is only one time constant, as for the first order system, in fact. For second order systems, that you can see here, it is the xi omega n expression that you can see here. And this expression corresponds, in fact, to a time constant that is equal to tau equals 1 over xi times omega n. I repeat, this is an innovation that I am bringing on control systems. I am saying that there is only one time constant for second order systems, whatever they can be, for any value of the damping ratio that you can consider and any value of the natural frequencies that you can consider, okay? This value, natural pulsation, excuse me. So this value, the value of the time constant for this system is tau equals 1 over xi times omega n. And then this value is a double of what I have defined like the relative time constant. We will come back to these notions. And going from there, this will take us in a wide exploration, and I will show you how we can derive these things in details for future videos. Okay, so let's now share with you the different profiles for these responses. You can see these here are only for autonomous systems. Of course, we can write this for initial responses, and all these I have done the hypothesis or assumptions that the initial conditions for the S of t and for its derivative value all are equal to 0. Okay, let's go now for their profile. So here you have when the system is not very damped, okay, is not enough damped. Okay, sorry for the expression. Sometimes I lose some words in English, etc. Coming back from French, coming back to French, going to English, etc. Sometimes I lose the correct and right expressions, but you can understand that this is what I want to say. It's clear. So when you consider the damping ratio less than 1, you have these behaviors in the response of the system. Here in yellow, just to see that what you have is a system that is not far from 1, with the damping ratio is maybe around 0.95. This is a behavior, and due to the bold lines that you have here, you won't be able to see the details here, okay? Let's go for this one, okay, where you have the damping ratio greater or equal to 1, critically damped, very strongly damped, and you have this kind of responses here, okay? So let's go again. Now I will be talking to you about the phase portraits that you have here. For example, for the system which is not critically damped. As I was saying, the system is living in a circular trigonometry, in a circular world, okay? And then when you move the system from its equilibrium and you release it, so the hypothesis for all following system, I will just be considering and studying and presenting systems that are stable. So when you remove the system with its dynamic, it will go to its equilibrium here, as you can see. On the x-axis, the axis, you have the variable, meaning s of t, and its derivative on the vertical axis. So going from any point, any given point here, the system will converge to the equilibrium here, okay? And it will depend on the value of a xi. Here you can see that the xi that we consider is let's say probably less than 0.5, okay? And then it will go and do some turns before it reaches the equilibrium. So from here, these are the solutions of our characteristic equation that I am presenting here. When you consider your differential equation, recall that expression that is here, this one. So from this one, you will have these values, okay? So this is the real part, and this is just the corresponding value. I don't put here the imaginary axis. I just put here like you are in a real plane. You will see, we will see and understand why. Let's go for another phase portrait where you have the system which is critically damped. You have the system is lying, as I was saying to you, on a line, okay, here, and the double pole is here, that is minus C times omega n. And from there, so what you have, the phase portrait is given here. You can see you leave any given position and with any given speed, and then when you remove the system from its initial condition, it converges to the equilibrium, which is in the center of the picture. Okay, so when the system is critically damped, what you have is that the system is living, remember, in a hyperbolic space or a hyperbolic world, and then the corresponding values of the solutions of your characteristic equation, corresponding values to the poles, remember the poles about which we talk for transfer functions. And then here you have one part, and the other, the complementary part also, it's here. Okay, what I was saying to you is that you can see that the expression and the way of presenting the things is exactly the same for the sinus world. You will be able to check it. Just rewind and then check what I'm talking about. So same remark, when you leave here, you will reach the equilibrium very quickly, okay? And then from there, here, what you can see is from that calculation, from the philosophy that I was saying. So look at here. This expression 1 over C times omega n, I say that this is the time constant of any given second order system. Whatever its damping ratio can be, whatever its natural pulsation can be, you will have this expression. And then from this one, I will compute all the coefficients that can make me reach a given percentage in terms of responses, okay? And then from this value, what you have here is that if you consider alpha r is equal to 1, it means that for any given damping ratio that you can have here, okay, you can find exactly the percentage of the initial condition from where you will be able to find its time constant of the system, of course. This is done for all these damping ratios. You continue here also from 0.55 to 0.97. And there is one that people use so much. It is this 0.7 that we have here. So now let's see with these formulas that I will be showing under simulation, how we can compute the time responses of a system, of any given system, of damping ratio equal to 0.7. This is what we have here. So this is the time response. Recall that I just consider the autonomous system, okay? But don't worry, it's very easy if you want to consider an initial response. You just consider this same expression for a percentage that is equal to 100 minus 2. Okay, it means 98%. So for this expression, we will talk about autonomous system, meaning the time response at 2%. For an initial response, we will talk about a time response at 100 minus 2, meaning 98%. So for an initial response, we'll talk about 95%, 100 minus 5, 90%, 80%, okay? And the formulas are here. These formulas, I have derived them from the fact that I have introduced, because until today, I don't see somewhere in any book that a given second order system has only one time constant, which is equal to 1 over c omega n. So until you prove that there is this definition that comes from somewhere else, I am okay to discuss with you. I agree to discuss with you. But I have never seen this since I have been studying control systems, okay, more than 20 years now. Maybe I am far away from the reality, but I don't know. But anyway, if you consider this expression, okay, so from this expression, I have derived all these constants, okay, that I am giving to you today, such that if you need a time response of a given second order system, you can derive them. You can do also the same for the rise in time that you can have, okay? If you want rise in time, the rise time, sorry, or the fall time, it will depend on your initial condition where you go from. And then to reach your equilibrium, if you go from a point that is above your equilibrium, you will be on a fall in time process. If you go from a given or a point that is a starting point to reach your equilibrium, and the starting point is under your equilibrium or the final value, you will be going from, you will be having a rising time, okay? So the indice that I put here is just to say in French, montée descente, but in English we say the rise and fall time, okay? And then this rise and fall time from 98% to 2%. Remember that, okay? When we talk about autonomous system, what we have is, for example, this one here. Or if you prefer this one, this in magenta, you have the most important percentage is the most close to your initial condition. So this is why we have 98%. And then after we have 2%, talking about the rising and falling time, okay? And then here, this is a constant, so you have 2.9 over omega n to compute the falling time from 98% to 2% when the damping ratio of your system is equal to 0.7. And then if you want to localize your time response, okay, not the time response, but the time constant of your system, you just position yourself at around 50%, and then you will find this value of the time constant of your system. You can see from this table that to localize the time constant of your system, according to this definition I have introduced, it is not always at the same value of percentage. Of course, you have different points at which you can find according to your damping ratio value. Okay? So all these computations are synthesized in this book, and this is the French version, but the English version is coming very soon. If I translate it, so I am the author of this book. If I translate this, it is dynamical systems, new vision, new paradigm, new methods for the characterization, identification, design, and control of dynamical systems. So this book will be ready, will be available very soon to for your commodity to be bought. So please prepare your money, and then I hope that you will be able to buy your own book, okay? And I will be giving you this as a bookmark, okay? So now let's go for some simulations through which I will be showing you how to proceed with these formulas. Let's just consider an example. Okay, so MATLAB, you are here. Let's go for this. Let's consider a system. Let's start with 0.7. Okay. If we start with 0.7, the simulation, so what I do, the philosophy is that I give here the values of Xi. I consider the omega n, which is the natural pulsation. I consider B2, which is B, it is a static, like the gain for the input. And I derive from there all the coefficients of the second order system after I give the initial conditions for the response, okay, autonomous system. These are for initial response. This is the input for the autonomous system. And from there, I derive the step, the ending time of the simulation. I compute all these elements. And after I launch this simulation, which is in reality here, okay? So this is a second order system that you can see here. And I can show you inside. So the inside is here, okay? This is a representation of the differential equations that I have shared with you. What I do is I launch this simulation from this, okay? And then I get a response. Of course, I plot the system. So I compute all the laws, theoretically laws that I have presented to you, and I match them with the results that I have from this simulation, okay? And from there, I compute the corresponding values of the time response and also the rising times that I have shared with you. This is what we are going to do. So let's go to do it for this damping ratio value. But all these values, I can derive the corresponding coefficients. And also recall that on this board, on this table, for all these tables, I have also derived all the corresponding coefficients and values that can be used to compute all these elements. Okay? So now let's go. Right, I launch the simulation now, and let's check what is happening. So simulation is going on here, as you have seen. Okay. Let me plug in my battery to avoid to be surprised. So the simulation result is here. Okay, have a look. And then we have the time constant here at around 50%. This is what we have. So now let's go and find it. 49.98. Okay. 49.98. The response is 0.5432. When we check here, this is exactly what we have for the time constant of our second order system. Okay. Recall that the damping ratio is equal to 0.7. And then from here, look at this. Here I have computed the omega n, which is a random value, randomized value. Okay. If I want to derive this value, I have to go and just apply the formula from here. That is tau equal to 1 over this. So if I have to derive the omega n, it is equal to 1 divided by Xi times tau. This is a calculation that we are going to do now. Let's do it. Let's just consider 1 over 0.7, that is a damping ratio, multiplied by this value, 0.5432. And then from there, the damping ratio, the natural pulsation is here. Okay, let's verify the value. So we have the omega n is quite exactly the same what we can see here. Okay, So from this formula, so now let's check the time response at 2% of our system, of our initial condition. Let's go for 2%. Go for 2%. We have the time response at 2%, which is equal to 1.1821, as you can see here. If I go here, it is here, 1.1823, 1.1821, you can see here, okay? So you can see that it is the same. Let's go again for the 5%. 5% is quite here. Let's try to give the good value. 1.1027. So you have it here, 1.1028. Let's go for 10%. So we reach 10% and it is quite equal to 1. So 10% you can see here. It's quite 1. Okay. Let's go for 20% of the initial condition always. And this is it. You have 0.8495. This is what you have here. Okay. And then let's check a bit just for the time, the rising time. This is a fall in time, I want to say. So if you go from 98% of your system, of your initial condition, 98%, from this value, we should reach how long will it take to reach the 2%? Okay. So it will take the difference between both. So let's compute it. Let's compute 1.1821 minus 0.0799. 1.1022. This is the time response between 18. Okay. So if I do this, okay, and evaluate, you can see that the two values are here. 1.1022, 1.1024. It's quite the same. Let's go for now the time response of 5%. 5% of the initial value. This is it, okay? And then let's check the corresponding value at 95%. 95% that we have here. Now the difference, 1.1026 minus 0.1304, and then this is what we have as value. It is a rise in time corresponding to this. And then if I just do this, putting here 5, putting here 5 also. So we have quite the same values. Okay. This is what you can see, right? And then this is just to show you according to the time response what we can have. We can compute it very easily. And then so you people most of the time use 0.7 in order to do their calculations. I have derived this to show you, but I can also use another one. Let's consider 0.3 because in the French example, I have considered 0.5. So let's consider 0.3 here. And then we go for it. So the damping ratio is equal to 0.3. And now we have the response of the system. Let's do the same exercise. I have to zoom. And just to keep the interesting part for us, yes. And then let's go and find a given point here. Let's check in the table for 0.3. What is going on? We have to be at minus 37.2 to have the time constant. Let's go for 37.2 minus 37.2. Okay. Minus 37.2, I say. Let's try to reach that point. Okay, let's say that we reach it. And then here, so the tau that we have computed is here. If you check the value, it is 0.59, let's say 51. It is quite the same that you have here. Okay, this is the position of the time constant of my system. Okay, the corresponding value is this one. So let's now go for the time response at 2% of the initial condition, 2%. What we will be having is its position that is here. 2%. And then from there, you have here the 0.2951. 0.2951. That is exactly what you have here. Let's go for 5% and check. I mean, do you like this method? Do you like this method? Leave me a comment, please. And then from here, what you have is that this value, 0.2871, this is what is here, okay? And then let's go for 10%. Very easy, very practical. 0.2742, 0.2742 at 10%. This is what we have. Let's check now for 20%. So for 20%, what we have is here 0.2498. 20% is here, 0.2497. This is what we have. And then if we want to check the time response, the rising time, we just consider this one to earn time. What we can see is that if we position ourselves here at 80%, okay, let's go again to find the 20%. Okay, here we go. We have 80%. And then after I consider the difference between both of them, 0.2498 minus 0.1053. This is equal to this value, okay? And then you can see that the rise time between both percentages that are 80% and 20% are quite the same. Only the last number is different, okay? So this is what I wanted to present you. And as I told you, it is possible to do the same thing for the others. So I hope that you have loved this video. So understand that this is a new vision that I have introduced for second-order dynamical systems. Only by putting in front a given definition and by stating that any given second-order system with constant coefficients, okay, has only one time constant that is equal to the inverse of the product, the damping ratio multiplied by the natural pulsation. Okay, only on that. So for the next videos, I will be able to show you the case for which the damping ratio is equal to 1 or greater than 1. So stay tuned, and I hope that you have enjoyed this video. You can already apply it in some other systems that you have. For example, an RLC system or serial RLC filter. You can apply this technique, this method to the regulation of speed, okay, for control motor, for example. Okay, not as a regulation directly, but you can check it for the open loop if you check the transfer function of a DC motor between the input that is a voltage and the output that is the velocity or the angular position. I think it can be the velocity. You can check the transfer function order. If it is a second order, you can vary the parameters and check what you will be having, like a time constant, like a time response, like a rise in time or a fall in time, at different values that you can consider. So I hope that you have enjoyed this video, and I say to you, see you next time, and I hope we will be able um, to exchange very soon. You will be able to listen again to this. So thank you very much, and then I say to you goodbye.